Okay, now we get to start talking about the periodic table and how it's put together. So this podcast is going to focus on the history of the periodic table and some of the basics of its organization. And we are going to be doing pages 2 and 4 today. I know that seems weird, but there's no actually any page 3 in the packet. So it's really just the first 2 pages of your packet. And you might notice that it's kind of a short packet compared to your normal size. It's only 12 pages instead of like 20. It's also a pretty short unit, so there's not going to be any quizzes. You're going to have a test in 2 weeks instead of like 3 or 4 weeks. So let's dig into it. First, starting with the history. The very first periodic table was put together in 1790. It really wasn't a table of elements. It was really more of a list of elements. There were only 23 elements back in the day. Then by 1870, a little less than 100 years later, we knew of about 70 elements. Well, now, over 100 years after that, we have 118. So we've got a lot of progress. And John Newlands was the first to start arranging elements by properties into something that looks a little bit like our periodic table that we see today. Now, the property that he cared about most was the atomic mass. It was easy to measure, and he saw that when he listed out the elements, he started to see these like increasing masses, and so he used that to kind of organize some of his elements. He also noticed some other similar chemical and physical properties that repeated when he did use atomic mass to order his elements, and so he called those periodic properties. It's kind of the start of the periodic table as we know it, in that name that everyone recognizes. Now, Moseley and Mendeleev came around a few years after Newlands, and Mendeleev was actually the first person to publish a periodic table, which is why he gets called the father of the periodic table, and he's kind of the big person that everyone knows, and Moseley isn't necessarily that famous. So, he did a good job, but let's talk about Mendeleev first. Mendeleev actually took Newland's rows that he put together and investigated more of the properties that he'd been studying and reorganized Newland's rows into his columns. Mendeleev studied compounds formed from the reaction of different elements with oxygen. And what he noticed, if I use X just to represent some random element, is that those elements sometimes formed 1-to-1 ratios with oxygen, and then there were other elements that you needed 2 of that element to react and form a stable compound with oxygen, and some others kept forming compounds that was like 2 of this element with 3 of these oxygens, and he saw this over and over again in these elements, and so he started to use those properties of how elements react with oxygen in order to classify them and put them in a certain place on the periodic table. So Mendeleev is also really well known and kind of famous because his periodic table left spaces for undiscovered elements. So he saw certain repeating properties, then he saw some gaps. And instead of trying to fill them in and make things work, he said, well, there must be some element we haven't discovered yet that's going to have these properties and fill in this space. And he was right. Now, other people named it, and he was a little off on some of the properties, but he was very, very close to a lot of them. And so he gets a lot of recognition for that. Moseley was the first to organize elements by their atomic number, which of course is how our periodic table is organized today. So he is a big contributor to this periodic table. But when it comes down to it, he didn't really know what the atomic number was. He didn't know that it was equal to protons. He had no idea what a proton even was back then. But he was able to find this unique number for each element, and he used that to organize his periodic table. So, our periodic table is organized using the periodic law. And the complicated long form of that is that when elements are arranged in increasing atomic number, there's a repeating pattern of physical and chemical properties. What that really means to us is that physical and chemical properties are a function of an element's atomic number. The atomic number determines everything, basically, about an atom. Now, we know that there's more to an atom than just the atomic number, the protons. The electrons have a big kind of say in how our chemical properties are expressed for given elements. So electrons have a big deal, but really those do come back to being equal to the protons for the most part. So it does all come back to that atomic number. Now, the arrangement of electrons in the highest occupied energy levels are always going to be similar for the same group. We've already seen that. The valence electrons are the same in the same group, and those are the electrons that have the largest role in determining chemical properties. Inner shell electrons barely influence things. So the way I think about it is that outermost layer of your clothes is going to determine how people act and interact with you. You got a really fancy jacket, people are going to treat you like a fancy person, even if you got a t-shirt and holy t-shirt underneath it. So electrons are important too. Now, there's this little section in here that starts to get into electron configuration stuff. So let's fill this in real quick. All this is really wanting you to realize is that on this first period of the periodic table, so period meaning the row, we only have one energy level, 1s, that's being filled. On the second row, second period of the periodic table, we still, even though we have two different types of orbitals, they're both on the second energy level of our atom. So those are both, if we simplify things down to Bohr's atom, 2s and 2p are still adding electrons to that second energy level. As soon as we get down to the fourth energy level, though, you'll see we're adding electrons to the 4s and the 3d. So that's when things start to get off. We're actually adding electrons to two different energy levels as we go across the fourth row of the periodic table. Same with the fifth row, two different energy levels on there. The sixth and seventh row have three different energy levels on there because they go down into the Fs. So all this is trying to point out to you, the only thing you need to know with this crazy table is that the energy level of my atom is not really the same as the period of the periodic table. They're similar, there's a lot of matchup, but it's not the exact same thing. One thing that the electron configuration does tell us, and does have to do with the periodic table, is that the length of the row on the periodic table is determined by the electron configuration. As soon as the electrons are full, those energies, those sublevels are full, then the row is full, and you have to start a new row. So that's the one way that they do really match up. So down at the bottom of the page, this is similar to what is going to be on your fourth element quiz. It's coming up pretty soon. So this is kind of a nice little review of these names, and there's a couple other names you need to be familiar with, but these are some special groups. This first group, first column of the periodic table, are the alkali metals, and they have super duper high reactivity. And that comes back to their electrons. Like we just said, the electrons determine the chemical properties. Because it just has one valence electron, all it needs to get happy and fulfill the octet rule is to lose that one electron. So it's going to go try shoving its electron into any atom that could possibly take it. It's going to be super reactive with anything and everything. The second column of alkaline earth metals also has a fairly high reactivity. They just need two electrons to go away before they can get happy, but they're not going to be nearly as reactive as those alkali metals. These metals are so reactive that you often don't find these just free elements in nature. You're not going to just walk along and find a chunk of sodium or lithium lying on the ground or dig it out of the ground because it's so reactive it will react with stuff and form compounds naturally. Over on the opposite side of the periodic table, our halogens in group 17 have the highest reactivity of our nonmetals. Very, very reactive, fairly similar to those alkali metals. The noble gases in group 18 are actually very low reactivity, and sometimes we call them inert, meaning that they do not react. Though we can kind of force them to react in certain situations, we generally regard them as non-reactive, inert elements, because they have those 8 valence electrons that everyone wants to be stable, so they don't want to gain electrons or lose electrons. They've got the 8 that they need. Now, little side note about helium, because helium doesn't have 8 valence electrons. I know that it's in that column there, it says 8A above it, but think about it. Helium is element 2. It only has 2 electrons, but similar to the rest of that column, those noble gases, it's full when it has 2. That's the most that 1s can hold. So even though it has a similar configuration with that 1s2 as the second column of those alkaline earth metals, the properties resemble group 18 properties, which is why it's over on the opposite side of the periodic table from the rest of the S2 elements. Now, talking about the blocks of the elements, and then top of the next page, page 4 supposedly, all of our S block, those first two columns, alkali metals and alkaline earth metals, are metals. And this is another place where we see kind of this weird exception, this hydrogen. It has a group 1 configuration, 1s1, which is why it's sitting over there at the top of the first column. But it's not a metal, which means it really doesn't belong over there. Technically, its properties resemble more of the group 17 properties, the halogen properties. So it could belong over there. It even can form a -1 charge like those halogens like to, but the electron configuration technically says it should be over there in the S block. So that's where it lives. The P block has metals, nonmetals, and metalloids. This is the most diverse block. And if you just think about this P block, just doing a quick simple sketch here, it has that stair step going through it. As you go down the P block, you're getting more and more of your metals and metallic character and less of your non-metals, just because there's more of them as we go down. So it has a lot of different properties, but as we go down that P block, we get more and more metallic. D block is our transition metals, transition elements, low reactivity, very stable in general. That's why all of the metals that we use for jewelry are in that transition metal area, like gold, silver, platinum, because they're low reactivities. Then our F block has our lanthanide and actinide series. Our lanthanide is the first row of the F block, the 4F, and actinide are 5F, and those are all radioactive and not useful for a whole lot of day-to-day stuff. But those are our special blocks and some of the special names for our elements in there. So there's this table. We're going to come back to this table in a minute. We just want to kind of talk about metals, nonmetals, and metalloids one more time real quick and their properties. So metals, of course, on the periodic table are to the left of the staircase, and they tend to be good conductors of heat and electricity. All of their atoms and electrons are just flowing and easy to move, so that heat and electricity can easily move through them as well. They are malleable, able to be rolled or hammered into sheets. Once again, the atoms can move easily. Ductile means it can be drawn into fine wire. And these metals tend to be solids. And one exception, of course, is mercury, Hg. Our non-metals are to the right of the staircase. They're kind of the opposites. Everything that's not a metal is classified as a non-metal. So they have poor conductors of heat and electricity. They can be solids, liquids, or gases. Like I said, they don't have a whole lot of common characteristics. They're just kind of not metals. And the solid form of these nonmetals tend to be brittle. So they're not as malleable and ductile as metals are. Metalloids have to be touching the staircase, except for Al, of course, is a metal. And they have some characteristics of both our metals and nonmetals. All of them are solids, and they are semiconductors of electricity, which gives them some useful properties for doing some interesting things, like being used in computer chips. So those are our classifications of our elements. You do need to be able to look at a periodic table and classify something as metal, non-metal, and metalloid. So maybe color code your periodic table, or at least draw this in there. Now back to that table up above. Go ahead and put these two X's in this place, because you're not going to be able to fill those spaces in. But I want you to practice using your periodic table to go through and identify all of these different traits of these different elements. And I'm going to do this first row with you. So this specific configuration, if I follow it to 2s2, 2p5, is pointing at fluorine. That is in the P block of the periodic table. The period or row is the second row. The group number is group 17, which has a special name of halogens. Those are non-metals over at the right-hand side of the staircase. And all of those halogens have very, very high reactivity, the highest of all of our non-metals. So You've got 3 more rows to fill out in the same way. Go through and fill this in. Just don't bother putting anything in those 2 spaces with X's. And I need you to do this in order for you to get your stamp. So fill in the rest by yourself. That's it. Have a good rest of your night.